Hi, everyone. So again, we're going to be starting our review of Chapter 3, and we're going to be doing it a little bit out of order in terms of the way the book presents it. We're going to be covering compositional stoichiometry first, and then proceeding to reaction stoichiometry towards the latter half of our review of Chapter 3. And essentially, when I refer to compositional stoichiometry, what I mean is the quantitative relationships between atoms when we're considering a chemical compound. So, for example, suppose that I am interested in studying sodium carbonate. Well, the formula of sodium carbonate is Na2CO3, and what it means, and we're all very familiar with what it means, is that I have 2 sodium atoms for every 1 carbon atom for every 3 oxygen atoms in sodium carbonate. But keep in mind, again, we know all this because we have a known compound in mind, we're well acquainted with its formula, and so it's very easy for us to sit there and quite simply determine the ratio of atoms that occur within that particular compound. Part of what we do as chemists is we frequently are presented with an unknown compound that we have to identify. And so when this occurs, a lot of times a common approach to identifying the compound is to at least gather the elemental analysis for that compound. So what that means is I'm going to, through a variety of experimental techniques, figure out how much of all of the different constituent elements are present for that particular compound. And usually that's expressed as a percentage, a percent composition. So it's important for us to understand how the percent composition relates to the formula, so that this way when we get this type of data, then we're better able to then go and eventually backtrack to calculate the formula. And we're going to be going over that procedure in greater detail tomorrow, the determination of formulas for unknown compounds. But in this particular case, let's actually review, and I believe this should be a review for most of you, let's review how to determine the percentage composition of a compound given the compound's formula. So usually, for example, if I'm trying to determine the percent composition for ethanol, the first step would be to determine the formula mass for ethanol. And if you recall, basically what you need to do is you need to go and tally up how many there are of each type of atom within the formula of the compound, and then multiply by that number times the atomic mass for each of the atoms. So for example, there are 2 carbon atoms. In ethanol, there are 6 hydrogen atoms in ethanol, and then there's also 1 oxygen atom in ethanol. And if I had a periodic table in front of me, I'd be able to see that basically the atomic mass for carbon is 12.01 atomic mass units. I have to multiply that by 2. I then add 6 times the atomic mass for hydrogen, which is 1.008 AMU, and then I'm going to add the atomic mass of 1 atom of oxygen, which would be 16.00 AMU. And if I go and add all of these terms together, then I should get a formula mass of 46.07 AMU. Now, as it turns out, I've done most of the hard work for determining the percent composition already, because to determine the percent composition for each element, all that I would have to do is to take each of these elements in turn and divide them by the formula mass of the entire compound. So, for example, if I wanted to determine the percent composition for carbon, I would take 2 times 12.01 atomic mass units, divide by 46.07 atomic mass units, and since I'm trying to find a percent, then I would multiply this ratio by 100. If I do that, I end up with a percentage of 52.1% carbon. If I'm going to find the percent composition of hydrogen in this compound, then I would repeat using the term that corresponds to hydrogen's contribution to the molar mass in the numerator of the ratio, divide through by the formula mass of the compound, again multiplied by 100, and end up with 13.1% hydrogen. And then if I repeat that once more for oxygen, I would take the term that corresponds to oxygen, divide by the formula mass of the compound, multiplied by 100, and I should get 34.8% oxygen. Now again, a good check would be to go and actually add all of the percent compositions together, and then that should give you 100%. And in general, this is a good starting point if I had an unknown compound, if I was actually presented with these percentages to work backwards and calculate formulas, which again we'll be reviewing tomorrow. And though it is absolutely important and imperative to understand the compositional stoichiometry of a compound, keep in mind the goal is to study chemical reactions. And in order to study chemical reactions, we remember from last year, and to be able to make calculations between amounts of reactants and products, then ultimately we need to be able to relate those substances to each other. And the way that we do that is by comparing the ratio of moles of each of these participant substances in a chemical reaction. And so we need to go and sort of review the mole concept one more time just to make sure that we have a firm grasp on it before moving forward. Now again, it's important to note that the mole is more than anything, in addition to being a concept that allows us to compare amounts of substances within a chemical reaction, the mole is also something that was born out of a sense of practicality. If I were to examine a chemical reaction equation, so for example, if I were to write the equation for the formation of water from hydrogen gas and oxygen gas, this reaction equation tells me that I have 2 molecules of hydrogen gas combining with 1 molecule of oxygen gas to give me 2 molecules of water. However, if I wanted to carry out this reaction, then I wouldn't, if I were going to do this in the lab, try and figure out some way to measure out precisely 1 molecule of oxygen and 2 molecules of hydrogen to combine together. Obviously, we must find a way to make things more practical and convert from the molecular and atomic scale to a mass scale that's relatable in the lab. And so that's also the other reason why the mole concept is also extremely useful. And again, just as a review, the mole concept is really just an issue of using this unit, the mole, as a counting unit. In other words, much like we have dozens of items, a dozen of eggs is 12 eggs, a dozen cars, that would be 12 cars. Basically, it's a unit in which we know that whenever we say the word dozen, there are 12 of those units. Well, the mole is similar in its application, though obviously the number in question is not 12. The way that the mole is designed, or I should say defined, is that it's defined as specifically the number of particles that are equivalent to 12 grams of a pure sample of, and this should say carbon-12, as in carbon-12, the isotope, atoms. Now, through experimental determination, we know that this number of particles is actually 6.022 times 10 to the 23rd atoms or molecules, depending on whether we're discussing elements or if we're discussing compounds, per mole. And again, this number is known as Avogadro's number. And Avogadro's number is a useful conversion factor when we want to go ahead and calculate the number of particles, be they atoms or molecules, in a mole involved in a chemical reaction. We'll take an example of that later on. But the mole concept in and of itself is also helpful because, as I said, it sort of bridges the gap between molecules and mass units that we can use in the lab. And the way that that happens is the following. We've been told that, again, 1 mole is equal to 12 grams of carbon-12 atoms. Okay? Now, keep in mind that by definition, 12 grams, or I should say, 12 grams of carbon-12 atoms are equivalent to 12 atomic mass units. And so if that's the case, if 12 grams are equivalent to 12 atomic mass units, that means that 1 gram is equivalent to 1 atomic mass unit. And that allows for us to make the equivalency, which you guys were aware of last year, that 1 AMU is also equivalent to 1 gram of substance per mole. And so this is what bridges the gap and allows us to be able to measure out precise and accurate quantities of substances and then relate those quantities to the mole scale. Now, as I said before, we're going to take a quick example in terms of how we actually mathematically convert between units of mass and moles and molecules. So let's take this example problem as a review. It says that I have a tablet which contains 325 grams of aspirin, which is acetyl salicylic acid, and the formula is provided. How many molecules of aspirin does this tablet contain? And so I'm going to start by writing out my 325 grams of my aspirin. Now, I want to convert these grams of aspirin to moles of aspirin. Okay? Now, that means I'm going to need to find the molar mass of aspirin, which is, again, the formula mass expressed in units of grams per mole. Now, if I do that, and if I go to the periodic table and actually do the same procedure that I did when I went and demonstrated the percent composition example earlier in the tutorial, I find that the molar mass of aspirin is 180.2 grams of aspirin per 1 mole of aspirin. Now, if I cancel units, now I'm in units of moles of aspirin, but I was asked how many molecules. Well, basically, the dimensional analysis is showing me that I'm currently in units of moles of aspirin, and I need to convert to molecules of aspirin. Okay, now, again, we know that there are 6.022 times 10 to the 23rd molecules of a substance in a mole. And so I would then insert Avogadro's number at this point in the conversion factor. And if I do this math, I end up finding out that there are 1.09 times 10 to the 24th molecules of aspirin in this tablet. Okay, so again, this should be somewhat of a review compared to last year. If anybody has any questions, by all means ask. When we come in tomorrow, we're going to go and work on some example problems. We're going to work on tutorials on mastering chemistry. I'll be circulating the room once again, just to make sure that everyone's all right. And if anybody has any questions, by all means, reach out via email, or if not, by all means, again, speak to me in class tomorrow, and I will see you guys then.